We'll start in 1 minute. In a few minutes, we'll start section 11.6 on absolute convergence and the ratio and root tests. But first, we'll finish section 11.5 on alternating series. So before we look at more examples, let's review the alternating series test. If the alternating series, the terms are -1 to the n-1 times b sub n, and the first few terms in the expansion are b sub 1 minus b sub 2 plus b sub 3 and so on, where b sub n is greater than 0. If this alternating series satisfies these two conditions, then the series is convergent. So the series of the b sub n terms need to be decreasing, and the limit of the b sub n terms needs to be 0. We were looking at this example on Wednesday. This is an alternating series. The b sub n terms are the natural log of n plus 1 over n, and they alternate from positive to negative and so on. One way to determine if the b sub n sequence decreases is to use a function f of x equals the natural log of x plus 1 over x. And we found that the derivative is x over x plus 1 minus the natural log of x plus 1 over x squared. And this derivative is negative when the natural log of x plus 1 is greater than 1. This term x over x plus 1 is always a little bit smaller than 1. And so in order for the derivative to be negative, the natural log of x plus 1 has to be greater than 1. So that's when x plus 1 is equal to e, or when x plus 1 is greater than e, or x is greater than e minus 1, which is about 1.7. So the terms in the series do decrease as n increases. And then we compute the limit of the b sub n sequence. So as n goes to infinity, well, we get an indeterminate form, infinity divided by infinity. And so L'Hopital's rule applies. The derivative of the natural log of n plus 1 is 1 over n plus 1. And we divide that by the derivative of n with respect to n, which is just 1. And this limit, as n approaches infinity, is equal to 0. So both of the conditions of the alternating series test are satisfied So we conclude that the series converges. Okay, the next example, the infinite series, the terms are -1 to the n minus 1 times 1 over n. And these are 1 minus 1/2 plus 1/3 minus 1/4, and so on. Well, this one is pretty straightforward. It's pretty obvious that 1 over n plus 1 is less than 1 over n. So the b sub n terms decrease. And the limit of 1 over n as n approaches infinity is equal to 0. So by the alternating series test, this infinite series converges. Yeah, that one was pretty easy. This is a somewhat famous infinite series. It's called the alternating harmonic series. So the harmonic series is perhaps more famous. The harmonic series is not alternating, but it's the series where the terms are 1 over n as n goes to infinity. So 1 plus 1/2 plus 1/3 and so on. So what do you remember about the harmonic series regarding convergence or divergence? So useful to remember, the harmonic series diverges. But the alternating harmonic series converges. So maybe you could jot down in your notes what does the alternating harmonic series converge to? I'll just say, what does this series converge to? I don't know why I did that. Question mark. So keep that in the back of your mind. And someday we will show what it converges to in class. Okay, let's move on to the next sheet. Determine if the following alternating series converge or diverge. Well, this is an alternating series. So can we use the alternating series test on this one? Okay, so the b sub n sequence is 2 to the 2n minus 1 over 4 to the n. So a couple of questions. Is the n plus first term greater than the nth term? And if it is, we want to know if the B sub n sequence is decreasing. So is B sub n plus 1 less than B sub n? And is the limit as n approaches infinity of B sub n equal to 0? Any ideas? Notice that this expression, 2 to the 2n minus 1 over 4 to the n. So note 2 to the 2n is equal to 2 to the second to the n, which is 4 to the n. So we can just look at the limit as n approaches infinity of 4 to the n minus 1 over 4 to the n. So what does that limit equal? Since there is a single term in the denominator, we can write this as the limit as n approaches infinity of 4 to the n divided by 4 to the n, which is 1, and then minus 1 over 4 to the n. 1 over 4 to the n goes to 0, and so the limit is equal to 1. So the alternating series test cannot be used to conclude that that's convergent. Okay, so what else do we do then? We have other tests like comparison tests. We might consider seeing if the test for divergence tells us something. So since we took the limit of the B sub n terms, that's without the alternating positive to negative and so on. And we found that the limit does not equal 0. What does the limit of the terms of the series equal? Okay, we found that this limit of the positive terms is equal to 1. What's the limit of negative 1 to the n plus 1 times 2 to the 2n minus 1 over 4 to the n? Well, when negative 1 to the n plus 1 is positive, these terms get close to 1. But when negative 1 to the n plus 1 is negative, the terms get close to negative 1. So that means the limit does not exist. Half the terms approach 1 and the other half approach negative 1. So the limit does not exist. Okay, it does not exist. And so we can use the test for divergence to conclude that the infinite series is divergent. So by the test for divergence, So if you need to review that, that's on page 713 in the textbook. So by the test for divergence, the series diverges. Because the limit of the terms in the series do not equal 0. Okay, let's look at the next series. The next one is an alternating series. Starting at n equals 0, the first term is positive, and then the second term is negative, and so on. Okay, so the b sub n terms are 1 over the cubed root of n squared plus 1. So does the b sub n sequence decrease? So is b sub n plus 1 less than b sub n? And is the limit as n approaches infinity of b sub n equal to 0? Are those conditions satisfied? If they are, then that means this alternating series converges. This one isn't too hard. Notice that b sub n plus 1 is 1 over the cubed root of the quantity n plus 1 squared plus 1. This denominator is bigger than that one, so that means the number is smaller. Okay, so b sub n plus 1 is less than b sub n. And then the limit as n approaches infinity of 1 over the cubed root of n to the second plus 1. The numerator is always 1, but the denominator approaches infinity. So that means the limit is 0. Okay, so by the alternating series test, the series converges. All right, one more example from section 11.5. So this is the infinite series. The terms are cosine of n pi divided by 1 plus 1 over n. This is just a semi-camouflaged way to write an alternating series. When n is 1, cosine of pi is negative 1. When n is 2, cosine of 2 pi is positive 1. When n is 3, cosine of 3 pi is negative 1, and so on. So if you want, you can make it more plain and write it as negative 1 to the n over 1 plus 1 over n. So it's pretty obvious anyway, but this is the more standard way to write an alternating series. So any ideas on whether this series converges or diverges? So somebody online, take a guess. Or if you've already computed it, type in what you found out. Okay, I got one answer. One says that it diverges. Okay, the B sub n terms are 1 over 1 plus 1 over n. Do you know how to simplify that? 1 divided by 1 plus 1 over n? Well, in the denominator, 1 plus 1 over n, we can write that as a single rational expression with a common denominator n. So this is n plus 1 over n. And 1 divided by n plus 1 over n is n over n plus 1. Okay, so the limit as n approaches infinity of the B sub n terms, which is just the limit of n over n plus 1, this limit is equal to 1. Okay, so the alternating series test does not apply to this alternating series. In other words, we can't conclude that it diverges or converges because the alternating series test conditions are not satisfied. Okay, but we can do what we did earlier. Compute the limit of the terms from the series. So the limit as n approaches infinity of negative 1 to the n times n over n plus 1. So what can you say about this limit? When n is an odd integer, so when for all of the odd integers n, the terms get close to negative 1. And for all of the even integers n, the terms get close to positive 1. So the limit does not exist. The limit doesn't exist. So by the test for convergence theorem, this series diverges. So make a note again, test for divergence. Page 713. So I keep emphasizing this divergence test, so make sure that you review that if necessary and just be aware of its existence. Okay, now we can go ahead and start the next section, 11.6. In section 11.6, we have what is called the absolute convergence test, the ratio test, and the root test. We start with a definition. A series where the terms are from a sequence A sub n. This series is called absolutely convergent if the series of the absolute value of A sub n is convergent. In the case that A sub n is greater than or equal to 0 for all n, then the absolute value of A sub n is equal to A sub n for all n. And in those cases, absolute convergence is the same as convergence. Here's an alternating series. The alternating series, the terms are -1 to the n plus 1 divided by the cubed root of n to the fourth. This series is absolutely convergent because if we take the absolute value of the terms, it becomes this series where the terms are 1 over the cubed root of n to the fourth. And this series is convergent because it's a p-series with the p-value equal to 4/3. So if it helps, 1 over the cubed root of n to the fourth is 1 over n to the 4/3. So this is just a p-series, and the value of p is greater than 1, so it converges. But with reference to the alternating series, we say that this alternating series is absolutely convergent. Okay, the next example, here's another alternating series. This series is not absolutely convergent because when you take the absolute value of the terms in the series become 1 over 2n minus 1. And we know that this series is divergent. You can show that this series of the absolute value of the other series is divergent by comparing it with this series. This one is just 1/2 times the harmonic series. And we always want to remember that the harmonic series is divergent. Okay, the next definition, a series where the terms are A sub n is called conditionally convergent if it is convergent but not absolutely convergent. Okay, so as we have already seen today, the alternating harmonic series is conditionally convergent. So that is, the alternating harmonic series converges, but the harmonic series diverges. So it's conditionally convergent. It converges, but it does not converge absolutely. Okay, theorem 3 from section 11.6 is going to be a useful theorem. This one says if a series with terms A sub n is absolutely convergent, then the series is convergent. So we'll do a sketch of a proof. So this given series, it could be an alternating series or not. But regardless of what kind of series it is, this will always be true. 0 is going to be less than or equal to a sub n plus the absolute value of a sub n. If a sub n is negative, then a sub n plus the absolute value of n is equal to 0. But if a sub n is positive, then a sub n plus the absolute value of a sub n is equal to 2an. But in general, we're going to say that this is less than or equal to 2 times the absolute value of a sub n. So this is true for all positive integers n, or all natural numbers. Okay, the hypothesis of the theorem, that's what's given. We're given that the series is absolutely convergent. So we're given that the series of the absolute value of the terms is convergent, or converges. So if we have a convergent series and then just multiply every term by 2, it's still convergent. So the series where we have 2 times the absolute value of a sub n, that also converges. And then using the comparison test, the series where the terms are a sub n plus the absolute value of a sub n, this converges by the comparison test because we're just comparing it with this series where the terms are 2 times the absolute value of a sub n. Okay, so the series of the absolute value of a sub n converges, and the series of the a sub n plus the absolute value of a sub n, that series also converges. And by a theorem in section 11.2, if we have 2 series that converge, then the difference in the 2 series, that is, if you subtract one of the series from the other, that will also converge. But in that theorem, it says that you can write that as a single series. So we have a sub n plus the absolute value of a sub n minus the absolute value of a sub n. But that just simplifies to the series of the a sub n terms. So this converges. See one of the theorems in section 11.2. Okay, so what we wanted to argue is that if a series is absolutely convergent, then the series itself is convergent. Make sense? right. Well, let's move on to this example. Test this series for absolute convergence. Hey, what are we looking at? We have the series. The terms are sine of 2n minus 1 times pi over 2 divided by n to the third. Okay, so this is just a semi-camouflage alternating series. Note that when n is 1, 2n minus 1, when n is 1 is 1, so we get sine of pi over 2, which is positive 1. When n is 2, 2 times 2 minus 1 is 3 pi over 2, so sine of 3 pi over 2 is negative 1, and so on. So this is just an alternating series. So we can write it so that it's more obviously an alternating series. So in the numerator, we'll just replace the sign of that expression with negative 1 to the n minus 1, and then divided by n to the third. Here, to test for absolute convergence, we just take the absolute value of the terms. So when we take the absolute value of the terms, we can just write this as the series from n equals 1 to infinity of 1 over n to the third. Okay, so what do we know about this series where the terms are 1 over n to the third as n goes from 1 to infinity? So what kind of series is it? Yeah, it's a p-series. The value of p is equal to 3 and it's greater than 1. So this series converges. So in other words, the original series converges absolutely. Therefore, the series converges. So therefore, by the theorem on the previous page, the original series also converges. Okay, so so just to summarize, if the series of the absolute value of a sub n converges, then the series of the a sub n terms also converges. So if the series converges absolutely, then the series converges. Okay, the next test is called the ratio test. So if we have a series, the terms in the series are from the a sub n sequence. If the limit of the absolute value of a sub n plus 1 over a sub n as n approaches infinity is equal to a number L that's less than 1, then the infinite series of the a sub n terms is absolutely convergent. And if it's absolutely convergent, then it's also convergent. Okay, in part 2, if the limit of the absolute value of a sub n plus 1 over a sub n is equal to L, which is greater than 1, or if the limit of the absolute value of a sub n plus 1 over a sub n is equal to infinity, then the series of the a sub n terms is divergent. And then a third possibility, if the limit of the absolute value of a sub n plus 1 over a sub n is equal to 1, then the ratio test is inconclusive. When it's inconclusive, we have to find a different method to determine if the series converges or diverges. Okay, so let's look at an example of a series and apply the ratio test. So the a sub n terms are n to the 10th over 10 to the n plus 1, or sorry, over 10 to the n. And so the a sub n plus 1 term is the quantity n plus 1 to the 10th over 10 to the n plus 1. Okay, so when computing the limit, the ratio test says use the absolute values, so a sub n plus 1 over a sub n. Note that we don't really need the absolute values here. Well, we don't need them at all because all of the terms are positive anyway. But we'll use the absolute values just to be in the right form. So in the numerator, we have n plus 1 to the 10th over 10 to the n plus 1, and then we divide by n to the 10th over 10 to the n. So in the next step, we'll go ahead and remove the absolute values, but we'll try to simplify this complex rational expression. So one way to do it, we can write n plus 1 to the 10th over 10 to the n plus 1 times the reciprocal of n to the 10th over 10 to the n. So that's going to be 10 to the n over n to the 10th. Okay, then we'll do some arithmetic inside the parentheses. Okay, so notice 10 to the n divided by 10 to the n plus first. I'm going to rearrange the terms a little bit. I'm going to write 10 to the n, and then 10 to the n plus 1 is the same as 10 times 10 to the n, and 10 plus 1 to the 10th divided by n to the 10th, that's the same as the fraction n plus 1 over n to the 10th. Over here, we can cancel 10 to the n divided by 10 to the n is equal to 1. So we can write this as the limit as n approaches infinity of 1/10 times n plus 1 over n to the 10th. Okay, can you see what this limit is going to be equal to? We can take it a step or two further. We have this constant 1/10 multiplied by n plus 1 over n to the 10th. So we can bring that constant out front and write it as 1/10 times the limit of n plus 1 over n to the 10th. Okay, now do we know what the limit is? Well, I was thinking about writing it as the limit of n plus 1 over n all to the 10th. But we can note that the limit of n plus 1 over n is 1. So 1 to the 10th is 1. And then 1/10 times 1 is 1/10. All right, so by the ratio test, since 1/10 is less than 1, by the ratio test, the series converges. The series converges. Okay, let's spend the last 4 minutes starting on the root test. The root test, if the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to L, which is less than 1, then the series of the a sub n terms is absolutely convergent and therefore convergent. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to L, which is greater than 1, or if the limit of the nth root of the absolute value of a sub n is equal to infinity, then the series is divergent. And then in part 3, if the limit of the nth root of the absolute value of the a sub n terms is equal to 1, then the root test is inconclusive. That would mean we would need to find a different method. Okay, so on this one, use the root test to test the series. The terms are 2 to the n over n plus 2 to the n. So we'll compute the limit as n approaches infinity of the nth root of the absolute value of 2 to the n over n plus 2 to the n. Once again, we don't need the absolute value symbols, so we'll remove those in the next step. So the nth root of 2 to the n is just 2. So in the numerator, we're just going to get 2. And then the nth root of n plus 2 to the n is just n plus 2. Okay, and we know what this limit is equal to. The numerator is always 2, but the denominator goes to infinity, so the rational expression goes to 0. So the limit is 0, and 0 is less than 1. So that means the series converges. Well, we have a few seconds left. Use the root test. So compute the limit as n approaches infinity of the nth root of 1 plus 1 over n to the n. So this is the limit as n approaches infinity. The nth root of 1 plus 1 over n to the n is just 1 plus 1 over n. And as n goes to infinity, the limit is equal to 1. So the root test is inconclusive. On Monday, we'll finish this one. That's all for today. So go ahead and sign in for attendance.